Okay, welcome everyone to today's applied math seminar, and we're happy to have Marwa Halabi today from Samsung AI Lab in Montreal. And so Marwa got her bachelor's from the American University in Beirut, and then went on to do a PhD at EPFL with Volkan Cever in 2018. And that was followed up by a postdoc at MIT with Stefanie Jegelka. And as I said, currently she's with Samsung within close collaboration with MILA. And she's going to talk about minimization of set functions, which are not submodular. So enjoy.
Thanks, Tim, for the introduction. So yeah, as Tim mentioned, so this is a joint work that I've done during my postdoc with Stefanie Jegelka at MIT. And I'll be talking about minimizing functions, set functions that are not submodular. So I'm not really gonna assume any prior knowledge on submodular minimization. I'll introduce the things that you need, and feel free to stop me throughout the talk if you have questions. All right, so just to introduce, so the problems we will be looking at are the problems where we're minimizing some set functions. So we have a ground set of elements V, and we have a function H, which takes subset of these elements and assign values, real values to it, which represent the cost of these items. And the goal is to select a collection S of items in V that will minimize our cost. Okay. And the reason we're interested in solving these problems, especially for me coming from a background of machine learning, is that actually a lot of problems in machine learning can be formulated as these sort of subset selection problems. And here I'm just showing some examples. This is obviously not these are not all the problems that we can see that are related to set function minimization. But some examples would be problems where we have a graph and we want to minimize the cut. So we want to select some nodes in a graph such that the number of edges that have one element in there and one outside is minimized. And these sort of problems come up, for example, in clustering and image segmentation. Other example would be, in some cases, we would be interested in minimizing the mutual information between variables that are indexed by the elements in set S and variables that are outside the set S. And these are problems that come up, for example, in graphical models learning and semi-supervised clustering. And then there's also problems that come up in structured sparse learning. And so these are problems where we have some observations and we're trying to select variables, which variables should be non-zeros in a way that will fit the measurements, as well as some prior structure where here F would be some regularizer. And then another example would be from batch Bayesian optimization, where we're trying to select elements. We have some function that we don't know how to optimize. We don't know the closed form solution of it, but we can query it. And we want to select queries in a way to optimize it, such that we minimize the cost of the queries while maximizing the information that we're getting about the function. So these are just some examples of where we have to solve set function minimization problems. And just to formalize things a bit, so this is the setup that we have. We have some ground set V of items 1 to D. And we have our set function, as I said, H. And we want to minimize H of S for any set S that is a subset of V. Okay. And typically, we're going to assume that H of the empty set is 0 without loss of generality. So we can just subtract usually H of empty set if it's not 0. And we only assume that we have access to this function via black box oracle that we can query at any input set S and will return the value of H at S. So we don't necessarily have the closed form solution of H. Okay. So unfortunately, solving this problem in its most general form is NP hard. And even further, obtaining any sort of multiplicative approximation was shown to also be NP hard. However, if the function has some nice structure, and namely if it's have something called submodularity property, which says that the function has this sort of diminishing returns property, which says that if you add an element I to a set A, then the change in your cost is bigger than adding the same element I to a superset B of A. So just as a silly illustration of this, you can think of this as H being the cost of your meal, and then A is the meal that you have, and the element that you're adding I is the drink. So the change of your cost when you add your drink to the meal is some H of I plus A minus H of A. And then if you add the same drink to a bigger set B, which already have the same drink, let's say, then the cost is smaller because maybe there's free refill or something like that. So this is just this sort of notion of diminishing returns. And the nice thing about this property is that it actually enables us to solve this problem exactly in polynomial time. So there's actually several algorithms that have been proposed in the literature to solve this problem either exactly or up to arbitrary accuracy. There's like both flavor of algorithms. And indeed, a lot of the problems that we encounter, set function parameterization problems that we encounter in machine learning are indeed submodular. But in this talk, I will be interested in cases where this is not the case. For example, in these examples that are provided, the two examples on structure sparse learning and Bayesian generalization, in this case, the objective function is not submodular. And we were interested in figuring out like if we can say something there other than like if the problem is usually as difficult as the general case. And in particular, we can observe that in this case, the objective is true is not submodular, but it's close to being submodular in some sense. And I will make this more formal later. Okay. So this is the question we were interested in looking at. So what can we, if there's other class, like a wider class of problems that we can probably obtain some approximation for the submodularity for the set function minimization problem, or is it just the case that only the submodular set function minimization problem can be efficiently solved? And prior work on this, we are the first one to look at the minimization of non-submodular functions, but there's been some recent interest in solving a optimization problem which involved maximizing non-submodular functions. The problem is that typically the techniques used for set function maximization are different than set function minimization. And in particular, they rely more on greedy sort of algorithms. There's also has been some work on minimizing set functions that are not submodular, but with some constraints. And in this case, it's actually the problem is much harder. Like even if the function is submodular, what we can do in that case is much weaker. Like the approximation guarantees we can get there is much weaker than the non-constrained version. So I'll be focusing really just on the unconstrained version of the problem. Okay. And in particular, we wanted to answer the following question: is if we take an algorithm that's used for submodular minimization and run it on a problem where the objective function is not submodular, can we say something about the solutions that we get? And spoiler alert, we show that this is indeed the case. We can show that one of the algorithms that's used for submodular minimization, and in particular something called projected subgradient method, can be also used to solve problems where the objective function is not submodular, but it's close to being submodular. And we provide approximation guarantees that will depend on the properties of the set function and how close it is to being submodular. Then we can show that this also can be extended to the noisy setting, where instead of having access to the set function itself, we have access to a noisy oracle of it. And then we can show that also the approximation guarantees we obtain with this algorithm are optimal in the sense that no other algorithm can improve on them, unless they use exponential many times. Okay. So let me start by first explaining what do I mean when I like to formalize a bit. What do I mean by approximately submodular functions? So there actually has been several notions of submodular minimization, approximately submodular functions that have been proposed in the literature. The one I'll be using here is something called weakly DR submodular functions. So we say that a function h is alpha weakly DR submodular if it satisfies the following version of the weaker version of the diminishing return property. So instead of satisfying this inequality exactly, we now have this extra multiplicative factor alpha. And if you recall, if the definition for when the function is submodular would correspond to having this inequality satisfied with alpha equal to 1. Okay. So if alpha is not equal to 1, then we say that the function is weakly they are submodular. And just to sort of give an intuition of how these functions might look like, I'm plotting here an example of a submodular function in blue and weakly the R submodular function in red. So in this case, this red function will have alpha equal to 3/4. Okay. So just in this case, the x-axis here is actually the cardinality of the set, so it's not the set. And then the y-axis is h of the s. And you can see that, for example, in this case, the red function, so it's actually a well-known fact that any concave function of the cardinality is submodular. So if we were plotting this as the x-axis being the cardinality function, we should expect to see a concave function if this is going to be submodular. So as you can see, the red function is not concave, but it's sort of close to being concave. And this is sort of like this notion of weakly DR submodular functions. Okay.
There's a question by Courtney. So what do you mean by noise for a submodular function?
I will make this a bit more formal later. So, but essentially, I mean, when instead of having the value h of s, you have a value h tilde of s, which will be an absolute value like far away from h of s, but an absolute value epsilon. So h of s minus h of tilde of s is less than epsilon.
Thanks.
Yeah. Okay, so the problem with using this definition is that if you notice that this will force our objective function to be monotone, either non-decreasing monotone or non-increasing monotone. In particular, if we have that h is an increasing function, we'll have alpha is less than or equal to 1. If it's a decreasing function, we'll have alpha greater or equal to 1. Okay, so this sort of, I cannot simply assume that my objective function is monotone, because that will make the solution of the unconstrained problem trivial. Like either it will be the empty set or it will be the ground set. So instead of directly assuming this property, I'm gonna assume this sort of, maybe from the first time to see this, it's sort of weird, but I'll show that this is actually general. So I'll assume that the objective function has a following form, that it can be decomposed into two functions, f and g, and both of them are non-decreasing, and f is going to be approximately submodular, so alpha weakly DR submodular. It will satisfy this inequality that I just showed you. And g is going to be approximately supermodular, which is, supermodular functions are just saying that so if g is supermodular, it means that minus g is submodular. And essentially saying that g is beta weakly DR supermodular is the same property as here, but with the minus sign applied. Okay. And we're gonna again assume that without loss of generality, that everything is normalized. So f of the empty set is equal to g of the empty set, and it's equal to 0. All right. So obviously, yeah, this looks like such an arbitrary assumption to make. So what are actually the functions that satisfy this form? And surprisingly, it turns out that any set function can be written in this form. So if you provide me with any set function h and any choice of alpha and beta, as long as they're not both equal to 1, then we can construct a decomposition. So we can construct functions f and g such that they satisfy the assumptions that I made. And actually stronger, they have stronger properties than that. So in particular, f and g are non-decreasing, and alpha weakly they are submodular, and g is also beta weakly they are supermodular.
Quick question. You told me that I can also decompose always as submodular minus submodular, right?
Yes. So like a prior result to this was that you can decompose any set function into the difference of two submodular functions.
Right. And are these then also, can these be chosen non-decreasing?
Yeah.
Okay.
Yeah.
Okay. Thanks.
Yeah. So yeah, like as Tim mentioned, there was already a result in the literature that shows that you can decompose any function into two submodular functions. But for me, this is not enough, because I need that the other function is close to supermodular and not submodular. And this is like what, and then my result is actually building on this previous result. And in particular, I will just briefly go over a proof sketch of it and sort of just to show how this is constructed. So just first to introduce some notation, we typically denote this change of the value of a set function as a marginal gain. So the marginal gain of adding an element I to a set S is written in this way. And then this epsilon h is characterizing how far h is to being alpha weakly DR submodular. So it's just the, remember that if we had that h is alpha weakly DR submodular, that means that this quantity here should be non-negative. And this epsilon h is characterizing how far it is from that. Okay, so to construct this decomposition, we start by choosing any function g prime that is non-decreasing and strictly alpha weakly DR submodular and beta weakly DR supramodular. So it means it will satisfy these inequalities. So it says from the definition of being beta weakly DR supramodular, you have this part of the inequality. And the definition of being weakly DR submodular is typically this one holds with inequality, but because we're saying it's strictly, it means that we have a strict inequality instead of an inequality. Okay, so like actually, so we can show that. So if alpha is strictly less than 1, then a simple choice to satisfy this would be just taking g of s equal to the cardinality of s. If alpha is equal to 1, then it's a bit more tricky, but we do provide an example in the paper of a function that will satisfy this. Okay. And then the way we construct this decomposition is as follows. So f will be the objective function that we had originally, plus some term here that will correct for the, that will ensure that f will have weak DR submodularity, and another term that will ensure that it is non-decreasing. And then g of s is just subtracting these terms so that we actually end up with h. So it's not too hard to see that from the way we chose g prime, this function will be weakly DR submodular and increasing, and the same thing for g. Okay. So a caveat here is that the constructing these f and g is in general anti-hard, and particularly that's because we're using this quantity here epsilon h, which is in general it means that you require to go over all possible sets to be able to compute it. But the good thing is that the algorithm that I'm gonna be proposing will actually not need to know the decomposition. This is only needed to provide theoretical guarantees. So before I go into what is actually the algorithm that solved it and what are the approximation guarantees we can provide, I'll just go over a brief overview of how we would have solved this problem, or at least one way we could have solved this problem if the function is submodular. And in this case, we rely on very nice connections between submodularity and convexity. So this is a known result from the literature, which is that if you have a function h that is submodular, then you can then minimizing the submodular function is equivalent to minimizing continuous relaxation of it, which is called the Levas extension. So the Levas extension is defined as follows: you take your input vector s. So this is a vector in dimension d, and you sort its entries in decreasing order, and then you just define this as the entry, the k largest entry times the marginal gain of adding this particular entry to the already k minus 1 largest entries. Okay, so you don't really have to worry about the definition, but just to give an intuition of what this is really doing, I'm plotting here a very simple example with dimension d equal to 2 only. And in this case, I'm plotting the set function as these black dots. And to be able to see why I can do this, so you can always think of a set function as a function of the vertices of the hypercube. And so in this case, this black dot at 0, 0 means this is h of the empty set. Then the black dot at 1 and 0 is h of the element 1, and then h of 1, 1 means h of the ground set, and like element 1 and element 2. Okay. And then just to give an intuition, what the Levas extension is doing is simply interpolating between these discrete values. And In this case, so the nice thing about this function when H is submodular is that it satisfies the following very nice properties. That if H is submodular, then the Lobas extension is convex, and this is actually an if and only if condition. And moreover, we can easily compute subgradients for this relaxation, which are given in this form. So it's just essentially you construct this vector which corresponds to these marginal gains. So computed the subgradient can be done by simply sorting and evaluating the function d times. So that means now we went from this discrete optimization problem to a convex optimization problem that we can use your favorite convex algorithm to solve it. And then actually rounding is very easy. You just look at all these sets as k's and pick the one that will give you the best set function. So you don't lose anything from going back to the discrete optimization problem. So now the question is, can we follow the same strategy when the function h is not submodular? And the first thing is that this equivalence between the two problems still holds. So we still have that minimizing the set function is equal to minimizing the Lobas extension, except that now the problem is that the Lobas extension is not convex anymore. So here's one example where, so the black dots correspond to a set function in V equal to 2 that is not submodular. And then now considering this interpolation thing, the function will not be convex. But the thing that we are able to show that is that if the function h is close to being submodular, then we can show that this Lobas extension is sort of close to being convex. And this is in the following sense. So we can show that if we use the same vectors that I said that work as the subgradient vectors in the submodular case, so these like kappa that is defined as the marginal gains of h, then this vector will can be shown to be a sort of an approximate subgradient. And this is in the following sense. So the definition, if kappa was actually a subgradient of h of the Lobas extension, then we would have this inequality holding with, instead of this term here that I wrote, it will be the Lobas extension of the vector S prime. Okay, so this is the typical definition of a subgradient vector. It means that you have this sort of lower bound hyperplanes on the function. Now, instead of having that, we have this other term, which is an approximation of the Lobas extension of S prime. And it will depend on this alpha, beta, and fng of how well you're doing as an approximation.
I have a quick question. So, of course, what you're interested in is the actual solution S star, right? But you have these equivalences of the optimal value, but how do you get, if you don't have an integer solution of the Lobas extension problem, how do you get the optimal set S back?
So so there's two parts to answer this. So first, like to get an integral solution for the discrete problem, you take the vector that you got from solving the convex optimization problem, and you look at these Sk sets, which were look at these like k largest entries of S, and pick the one that have the largest, the smallest discrete value, so the smallest h of Sk. And that is guaranteed to be epsilon away from the optimal h star. But there's actually no guarantees that you will get the optimal S star, because actually it might not be unique. You might have multiple ones that will satisfy the same value. Right.
And then one comment maybe for people who are very new to this, like I was a week ago. So this Lobas extension of H that's not even just a definition that follows from the properties of the Lobas extension, right? Because the Lobas extension is a linear operator.
Like you mean the definition that I showed before?
No. I mean, above you define that H sub L is F sub L minus G.
Yeah. Right? This is not the definition. Yes, it follows from the properties. Yes, exactly.
Yeah. Thanks.
Yeah, this is one of the nice properties of the Levi's extension, is that the Levi's extension of like the sum of two functions is this like the Levi's extension of the first one plus this Levi's extension of the next one. So yeah, now that we so this is like essentially the main result, is that we can show that this vector is still an approximate subgradient of the Levi's extension. And this is sort of what I mean when I say if H is close to being submodular, then the Levi's extension is close to being convex. And then one nice thing about this is that again, like this is the same vector that we were using as a subgradient for the submodular case. So this is again can be computed efficiently by just doing sorting and evaluation of the function. Okay, so now equipped with these approximate subgradient, we can do the same algorithm that is used in submodular minimization, which is projected subgradient method, which works as follows. So we start by a point in the hypercube, let's say all zeros, and then you take a step in the direction of this approximate subgradient kappa. Then you project back into the hypercube, and so on and so forth. You keep doing that for some t iterations. Okay. So now, because these are not the actual subgradients of the objective function we're trying to minimize, we're not going to actually converge to the optimal solution, but we're going to converge to the approximation of the optimal solution. And in particular, we have the following result. After t iterations of this algorithm, we can guarantee that the solution, the value of the reverse extension at this vector will be at most this multiplicative or sort of bifactor approximation of the optimal solution, plus some additive term that will go to 0 as t grows. Okay, so we're not gonna worry too much about the additive term. If you run the algorithm enough, this will be small enough, so we don't worry about it. The main thing is this multiplicative term. And again, like to translate this approximation guarantee to the discrete problem, we do the same exact rounding that we do in the submodular case. Like look at the entries of S, sort them, and then look at the sk and a set that will have the best set function value. And in doing that, we get the same approximation guarantee on the discrete optimization problem. So the nice thing about this is that it is a sort of approximation. So for example, you first would expect that if the function h is submodular, we should again obtain the usual guarantee that we get the optimal solution plus some additive error. And this is indeed the case. If h is submodular, then we have alpha equal to 1 and beta equal to 1. And then we have here h of the S star, so the optimal solution. And then the further you are from being a submodular, then the worse this approximation guarantee is. Okay.
I have a quick question.
Yeah.
So in the big O of 1 over square root t, is there some constant that depends on h hidden there, or
yeah,
is just
there's the Lipschitz constant of h, which actually I can provide a bound on it. It's related to the maximal value of h, basically. Yeah, maximum value of h. Yeah.
Makes sense. Thank you.
Isn't it like just the diameter of the base polyhedron?
I was gonna no, it's the diameter of the hypercube in this case, and I was gonna say like you also have the Lipschitz constant also the diameter of the hypercube. So there's like a square root dimension here.
Okay.
Yeah. Okay, so as I said, like if h is submodular, we get the optimal solution. Another nice thing about this is that we don't need to know alpha, beta, f, and g, because as I said, this is important because these are usually very hard to compute, and we just know h here. So one caveat that you might have noticed in what I said, I just started this talk by saying, oh, there's this set of problems that are very hard to solve and even to approximate, and then I'm saying now, we're going to assume some properties that actually hold in generality, and here's some approximation guarantees. So the catch in that is that if these values of alpha and beta, or like the way f and g are related, are bad in the sense that this upper bound is bigger than 0, then this approximation guarantee is not telling me anything. It's just saying that the value I'm obtaining is less than 0, which is trivial because I could have also just set S hat to be the empty set. And because I assume that my objective function is 0 at 0, I'm saying, oh, I'm going to do better than just picking 0. So I didn't tell you anything. But if the function is actually close to being submodular, then this upper bound will not be close to 0. It's actually going to be positive, and this is actually giving you some approximation guarantees. Okay. Any questions? Okay. So natural question to ask here is that can we actually do better than this approximation guarantee? And it turns out that we cannot, and at least in this general setup where we only have access to the value oracle model, where we only have access to HVBA black box oracle. In this case, we can show that for any choice of delta, no deterministic or randomized algorithm can obtain a solution whose expectation value is better than the approximation guarantee that I showed you by any factor delta, unless it uses exponentially many queries. Okay, and I'll quickly go over. I don't know how much. How are we doing on time? Okay, good. I think. Yeah, so I'll quickly go over the proof sketch of this just to give an intuition. So these are sort of the same, same strategy of showing like these sort of lower bounds for these algorithms. And in this case, it's showing that if the algorithm cannot query exponentially many queries, then we can fool it to think that it's minimizing another function than what it is really minimizing. And in particular, we can make it think that it's minimizing the 0 function. So to do that, we can construct a function h that will depend only. So first, we're gonna take our ground set and take a random partition of our ground set into two sets C and D, which have both of them will take half the size of the ground set, and we're gonna construct a function h that will only depend on the value of a set S on the intersection of these with these two partitions. Okay. So the value of h will be 0 if the set S has a similar number of elements in C and similar number of elements in D. So like it's called balanced set. And otherwise, it's some other constant which is negative C, and I will tell you what it is. But the important thing is some negative constant. Okay. So it's not too hard to show using sort of a concentration bounds that no algorithm can distinguish between this function and the 0 function, which takes only 0 for any set value, for any input set, unless it uses exponentially many queries. And because of that, then it means that if I run any algorithm on H, it will return as a solution the value 0 because it thinks that it's minimizing the function 0, while the true optimum is negative. Moreover, if we now use the decomposition result from that I showed you before, we can decompose this set function into two functions f and g that will satisfy our assumption. So this does fit in the framework that we're considering. And in particular, if we look at this approximation guarantee corresponding to the resulting f and g, these would be negative, while the value returned by any algorithm will be 0. And this sort of just proves what we mentioned, that no algorithm will be able to improve on this approximation guarantee. Okay. So before I show some numerical examples, I just want to briefly go over the setting where we have some noise. This is coming back to the question of what I mean by noise. So we're assuming that we have an approximate oracle h hat, which takes some input parameters epsilon delta, and it will return for any input set S, it will return a value h hat of S, which is epsilon far from the true value h of S, with some probability greater than 1 minus delta. Okay. So one example of how we can obtain these approximate oracles is that, let's say we have your function h, but instead of actually having access to h itself, you have some multiplicative noise, which could be some Gaussian noise or anything. But we have to assume that the noise is bounded. Then if you now construct the following approximate oracle, which is just sample this oracle multiple m times and then average over your samples, then this will give you the approximate oracle that I assumed if you take enough samples. Okay. So now, given this sort of approximate oracle, we can still run the same algorithm and with some choices of epsilon and delta, and we end up with the same approximation guarantees, but now they will hold with in a probabilistic way, not deterministically. So it will hold with probability 1 minus delta prime, and then you can ensure to get the desired additive error and probability by choosing the input parameters of the approximate oracle. So this is saying that if you have a noisy oracle, you can still get similar approximation guarantees, except now it's more expensive because you need to sample your noisy oracle multiple times. And in particular, it's showing that you need quadratically many samples. So you can see like there's a dependence on d squared here. But in practice, we see that this is not really the case. You can get away with much fewer samples. So just to show some examples of how this works in practice. So I'm going to consider here 2 examples. One example would be, so this one would be an example of a problem where the set function that we're trying to minimize is not submodular, but is approximately submodular. And I'm going to show after that an example where the function is submodular, but we have a noisy oracle. Okay. So for this one, we're considering a problem which comes up in, which is a structure sparse learning problem. So we're trying to learn a parameter vector x naught, whose support is an interval, which means it's like consecutive non-zeros that there was no like delay between them. It's just like, for example, in this figure, it's like multiple non-zeros and then all zeros outside. Okay. And we want to learn this parameter vector from noisy and linear Gaussian measurements. So we have y, which is equal to ax plus some noise. And A is a matrix, it's a fat matrix, so you have n, which is much smaller than dimension d. And it has the entries which are random Gaussian entries. So the goal is to recover these 2 parameter vectors of x naught. And one way to do this would be to solve the following optimization problem. So we want to minimize h, which already have the decomposition form that we want. We don't really need to find the decomposition. So in this case, G is characterizing how well we're fitting the observation. So in particular, it's equal to the minimum of the loss, which is a least square loss, restricted to the support S. And that's why this is a set function. And then F is a regularizer, which is trying to enforce the structure that the X that we're looking for should have an interval support. In particular, it's penalizing the largest entry in S minus largest index and S minus the smallest index in X. So to kind of encourage S to be contiguous. So in this case, the function F is actually submodular in this case. So alpha would be equal to 1. But the function G is not supermodular. But we can show that it is beta weakly. They are supermodular with some beta which is strictly greater than 0. And like how large beta is would depend on the condition value of A. Okay. So I'm showing here the results for running the proximal gradient method compared to solving this optimization problem by brute force, just going over all possible sets and finding the solution. And I'm plotting here the x-axis is the ratio between the number of measurement n and the dimension d. And the y-axis is the estimation error. So how well we're actually approximating the true parameter vector. So as you can see, as this number of measurements increase, the proximal gradient method is doing better and better, and eventually matching the performance of the solving this problem via brute force. And this basically is the expected behavior. And as you can see, so the reason why this happened is that as the number of measurement increase, the condition number of A increase, and it means that the parameter beta will increase. And then the objective function that we're trying to minimize is becoming closer and closer to being submodular. And that means that, as expected, the proximal gradient method will perform better and better, so closer to the optimal solution. Okay. So just to show also in terms of like actual objective value, I'm plotting here So I'm fixing the number of measurements here, which is n equal to 306. So this is in the regime where we're already close to being submodular. And in the x-axis here, I'm varying the regularization parameter lambda, the problem. And the y-axis here is the objective value. So as you can see, for all choices of lambda, we're always pretty much getting exactly the optimal solution. Okay. Any questions before I move on to the second numerical example?
I just have curiosity about this, the interval sparsity. Is there any application of this model in mind that you had, or just kind of a
yeah. So like one example where you could want something like that would be like that was another example. Yeah. I haven't applied it specifically on something, but sometimes like you wouldn't really use intervals. You would use rectangles, and then like in sort of computer vision, if you want to have like you can choose in the rectangles in a way to end up with a like if you're trying to select, for example, a support which is like trying to identify an area in the image which is a rectangle, then you can choose this to be, so you can change the regularizer to make this encourage a rectangle as opposed to an interval, and then you can get something like that. I forgot there was another application, but yeah, I haven't really tested it. So this is toy dataset. I haven't really tested it on real dataset. Yeah. Okay, and then so if we now go to the other numerical example, so this is in this case, I'm gonna consider a problem where the function is submodular, but now we have some noise, and in particular, we have multiplicative noise, which is Gaussian, with some variance sigma square, okay? And to construct the approximate oracle, I'm gonna just sample over m samples and average the result, and just plug in this approximate oracle into projected gradient method. So in this case, I'm showing the performance of several algorithms, classical algorithms that I use for submodular minimization, and not only projected gradient method. And then, so in particular, this is, okay, so like these are, if you're familiar with them, you would know them. So this is like minimum point algorithm, conditional gradient method, or like Frank-Wolf method, if you know this one. And then this is the projected gradient method, either with a step size that is decreasing with the number of iterations, or another way to compute the step size called Polyak method. And these other two are cutting plane methods. So we were basically interested to see if we take these like classical algorithms that could be used for submodular minimization, and if we add noise, how well they would still do in this case. And we can see that they're all sort of robust to noise, and in particular, I'm plotting here how far they are to the actual optimal solution, and the x-axis is the number of samples. And we can see already by taking around 250 number of samples, we're almost at the optimal solution with like some very small error. While, for example, in our bounds, it was the number of samples that you need would depend on the dimension square. So this is actually much smaller than the dimension square. Okay. And then, yeah, so that's it. So like just as a conclusion, so this work we try to show that that if you have a set function minimization problem, you could still have some properties such as approximate submodularity that allows you to obtain optimal approximate solutions with some guarantees on how far you are from the optimal solution using simple methods like efficient convex minimization algorithms. Thank you.
Yeah, thank you. I think we have plenty of time for questions. So if you have questions, then please feel free to unmute yourselves or write in the chat. So maybe I'll just get it going. So I'm still trying to understand these approximate subgradients that you're computing, I'm wondering, is it clear that they're not subgradients of the convex, what do you call it, convex closure of H? It's not a trick question.
Yeah. I'm trying to
don't know the answer.
It's not clear in the sense that I cannot tell you like, no, for sure, this is not the subgradient.
Yeah.
But also, it's not clear that they are the subgradients of
yeah, of course. No, I think I would have never thought of it if it wasn't for this one representation of the convex closure that you have, where it's a max of these inner products, and then there's this row term where you can wiggle. So
yeah, so actually, like I can actually say more. Like I haven't proved this, but I'm pretty sure that this will not be the subgradient unless the function is submodular.
Right.
Okay. Because of this other, like I don't have it in the slides, but in the paper I've written the form of the convex closure as a also maximization over the base polytope. But in this case, you have this rho parameter. I don't know if you have it. So if rho in the optimal solution for this is 0, then that would be a subgradient. But in general, that would not be 0.
Well, then it could be an epsilon subgradient. Okay, so but this is something we could discuss offline.
I see what you mean.
Are there more questions? Okay. If there aren't more questions, then let's all thank the speaker again.